In lesson 6, we're going to take a look at complex numbers and how they apply with radicals. So the first thing is a definition of an imaginary number. And if you remember back in our first unit, we talked about the different types of numbers, and we had the real number system, and then there was the imaginary part. Now we're going to take a look at the imaginary numbers and how to do operations with them. So imaginary numbers, you have whenever you have a negative underneath a square root, it becomes an imaginary number. So I is the imaginary number, and it's a number such that I equals the square root of -1. So another property is if I were to square both sides, you get that I squared equals -1 because the squaring and square root undo each other. So I squared is equal to -1 is another property that we could look at too. Another rule that we should make note of is that if a is a positive number, then anytime you have a negative under square root, it's the same thing as writing I times the square root of that number. So if we look at these examples here, if I have a negative under the square root, this is the same thing as saying I times the square root of 25, which we know the square root of 25 is 5. So this is like I times 5, but normally we write it with the 5 in front. So then this next one, if you imagine there's a negative under the square root, so that means there's going to be an I. If you take the square root of 49, you get 7, so the answer is just going to be 7I. This one down here, if we take the I out, we're left with the square root of 12, which we know we can break up, and we just keep the I out in front, kind of as if it was just like a number out in front. So the square root of 12, you can break up as 4 as the perfect square and times 3. So it becomes I times 2 times radical 3. And then we would just rewrite this as 2I radical 3. And then the last one here, this 17 doesn't break up any further. So this one's just going to be left as the square root of 17 times I, just to get rid of that negative. You don't ever want to leave a negative in your answer under a square root, so you just make sure you got to remember to do the I. Another thing that we can do with I is break down higher powers, because if you look at the powers of I, meaning I to the first, well, that's just going to stay I to the second we saw up top was -1, because the square root of -1 is I, so if you square both sides, you get I squared equals -1. I to the third is actually going to be -I, and that's because I to the first times I to the second. This is really the same thing as saying I to the third, because when you multiply, you add the exponents. And then I to the 1 is just I to the second is -1, so that's how it becomes -I. And then the last one here to look at is I to the fourth. I to the fourth is just going to be 1, because I to the fourth can be rewritten as I squared times I squared, which is -1 times -1, which is 1. And then after this, the pattern's just going to repeat. So I to the fifth is going to be, it's just going to bounce back up to here. It'll be I to the sixth, I to the seventh, I to the eighth, I to the ninth, I to the 10th, and so on. So the pattern's just going to keep repeating. So really the only 4 that you have to know are these 4 here. And if you wanted to rewrite, like say I to the 30, so looking over at this example, if I want to rewrite that or simplify it as much as possible, the easiest thing to do is to look at it as um, my exponent. How can I rewrite it so that it has I to the second in it? So I to the second. So if I divide the exponent by 2, so that's what I'm going to do. So divide exponents. You might have done this with dividing by 4 too, but sometimes I think it's easier to divide by 2. So divide exponents by 2. So if I look, I can rewrite this as I squared all raised to the 15, because 2 times 15 gives me 30. And if you remember your exponent rules, as long as you're raising to a power, you multiply the exponents. And then from here, I squared is -1, so I replace my I squared with -1 raised to the 15. Well, if you raise a negative to the 15th power, or an odd number of times, it's going to stay negative. Where if we raised it to an even power, it's going to become positive. So then if you look at this next one here, first I have to think about how can I rewrite 11 so that it has 2 in it. So the answer would be I to the second times 5, because, or raised to the 5th, which means 2 times 5 gives me 10, but then I need a plus a 1 to get 11. So this would be I to the first. So if you look at my exponents here, when you raise to a power, you multiply. So 2 times 5 gives me 10. When you multiply like bases, you add the exponent. So if I have 10 here plus 1, that's going to give me my 11. So then what I do is I simplify this. So I squared is -1. I to the first is just I. So -1 raised to the 5th is going to stay negative, times I, which is going to be -I. So see how we're always getting at one of these answers over here? It's because all of these are, it's like the pattern for the powers just repeat. So I to the 11th, I could really go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and see how 11, I to the 11th really occurs there. So it's the same answer. But when you have things like 40 or 30, that's a lot to count. So you could count it out, but you could also just use these properties. So I to the 40, I could rewrite as I to the second times 20. So this would be -1 raised to the 20, which is just going to be 1 since it's an even power. So that's it with imaginary. The next thing is looking at a complex number. So a complex number is when we have any number that can be put in the form a plus bi, where a and b are real numbers. A plus bi is also called standard form. The number a is the real part, and bi is the imaginary part. So basically, you can rewrite something in a plus bi form, where the bi part, because it has the I in it, is the imaginary part, and the a is just going to be some real number. So down at the bottom here, I'm going to just cross this off and write complex numbers. And then this is just a chart for you for reminders of what these different things are. So we have real numbers, numbers that you've seen before, any number that you've seen earlier in math. Complex numbers means you have a real number with a complex or imaginary part. And then pure imaginary means it's just something with I. So basically all the previous examples have been pure imaginary because all of them just had an I in them, where the complex numbers have to have addition or subtraction between the real number and the imaginary part. So now we're going to look at operations with these imaginary numbers. And before we do that, we just have this other rule to take a look at, that if I have this rule here where a plus bi equals c plus di, that's true if and only if a equals c, so these two parts have to be equal, the real number parts basically, and the coefficient in front of the I have to be equal. So two complex numbers are equal if and only if the real number parts are equal and the pure imaginary parts are equal. So if I want to look at this example, I want to find x and y if these two complex numbers are equal. So what that means is this part and this part have to be equal. So 3x has to equal 12. And this part and this part have to be equal. So 4i has to equal 8yi. So then what you can do is we can just solve these. So for this one over here, divide everything by 3. So x equals 4. And then on this side, I don't really need these i's anymore. So I'm just going to rewrite this as 4 equals 8y, just because you have an I on each side, so they really cancel. So then divide everything by 8, so we get 1/2 equals y. So that's it for that. Same thing for this example here. Um, we want to find x and y if these two complex numbers are equal. So we have this section is equal to the real number section. So 4x minus 3 equals 5. And then we have the 7i equals the imaginary part of this one. So 7i equals 2y minus 1 times I. So again, I'm just going to get rid of the i's because they just cancel out. You divide them and they cancel out. I divided by I is just 1. And then I'm going to solve these. I'm going to go ahead and finish this one up. So add 1 to both sides. So we have 8 equals 2y. Divide everything by 2. We get 4 for y. And then over here on the other side, we add 3 to both sides. So 4x equals 8. Divide everything by 4. We get x equals 2. So that's it for that one. And then the next property is when you add. So this is for adding or subtracting. The rule for adding and subtracting complex numbers. So basically, what happens is when you add and subtract, you're going to combine all of your i's, or all of your real numbers, and then all of your numbers in front of i's. So if you look at this part here, it's basically just like when you add or subtract polynomials, radicals, you combine your like terms. Same thing here. So we're going to combine our like terms. So we have 3 plus 7. It's going to give me 10. And then here, we're going to combine the 6 and the 4. So 4 minus 6 gives me negative 2. And then you're just going to keep the I. So it's just like kind of like a variable, like the I, you just treat it as like an X and just combine that. So same with this one. Combine the 7 and the 5. Before we do this, let me actually distribute this. So I'm going to have 7 plus 3i minus 5 minus 6i, just so we remember the signs. And then we can go ahead and we can combine these. So we have 7 minus 5 gives me 2. Then we have 3i minus 6i is going to give me minus 3. And then keep the I. And then same with this one, I'm going to go ahead and distribute that negative. So I have 5 minus 2i, I can drop those parentheses, distribute the negative, and then you just combine your like terms. So we have 5 minus 9 gives me negative 4, negative 2 plus 4 is going to give me plus 2, and then keep the I. So that's really it for adding and subtracting. It's really just combine your like terms. So combine the a and the c values, which are your real number parts, and then combine the b and d, which are the coefficients of the imaginary numbers. The next thing is multiplying. We're going to treat this the same way. We're going to apply the box just like we did when we multiplied binomials with x's. So it's basically the same thing. The only difference is you have i's, and you just have to remember that I to the second can reduce to negative 1. So we have, or any other powers of I you can reduce. So go ahead and you just multiply. So we have 6, we have positive 15i, negative 8i, and then here we're going to have negative 20i squared. So then I'm going to go ahead, I'm going to rewrite that. So 6, get your like terms. So we have plus 7i when we do 15 minus 8, and then minus 20i squared. But whenever you have an I squared, you want to remember that that reduces. So that's going to actually be a negative 1. So then this becomes 6 plus 7i plus 20, which means now I can actually combine these two numbers here. So I get 26 plus 7i. And again, remember, we always write the real number part first so that it's in a plus bi form. So that means the 26 would come first always. For this one here, it's just a distributive property. So we do 2i times 4 is going to give me 8i minus 12i squared. So it's basically just thinking of your I as like an x. The only difference is you have to remember that I is not a variable, it's a number, so it's an imaginary number. So that means I to the second I can actually rewrite as -1. So you just have to remember to reduce that. So 12, put in the -1, so we get 8i plus 12. And then to make this a plus bi form, you just have to flip these. So that's it for that. And then this one here, if I'm expanding this example, this remember is the same thing as 3 plus 5i times 3 plus 5i. So I'm going to set up the box, and then you go ahead and multiply. So we have 15i, 15i, and then 25i squared. So we have 9 plus 30i plus 25i squared. 9 plus 30i plus 25. You can rewrite that as a -1. So now I have 9 plus 30i minus 25. So now you're going to do 9 minus 25, which gives me -16, and you want that to come in front so that this is an a plus bi form. So one last example with multiplying. So we have set up your box. So 2 minus 3i, 2 plus 3i. So we have 4, 6i, -6i, and -9i squared. So when you combine your diagonals this time, what happens is your terms cancel out in the diagonal. And the reason why this happens is because these two expressions are complex conjugates. If you remember when we talked about conjugates before, it meant that you had plus or minus like the same radical. So it might have been like 1 minus radical 2, 1 plus radical 2. When it's complex conjugates, it means everything's exactly the same. It's just you have a positive and a minus between them. So that just means that these middle terms are going to cancel. The 6i will always cancel out with a -6i. So then what you're left with is really the first and the last terms if you were to multiply. So 4 minus 9i squared is what I'm left with, which is 4 minus 9 times -1. So 4 plus 9, which is 13. So basically what's going to happen with these complex conjugates is that the i's are going to cancel. So you're not going to have any imaginary part because the only imaginary part you're left with is the I squared, which is going to become -1. So you should always be left with just a real number. And that's what this property down here is saying, is that whenever you have complex conjugates, when you multiply them, you're going to be left with a squared, so the first terms and the last terms. But it's really going to be just plus b squared because the I, first it becomes minus b squared times I squared, but I squared becomes -1. So essentially in the end, it just becomes a squared plus b squared. So let's look at two examples of how to use these, and then that'll be it. So you're going to be using complex conjugates whenever you're dividing, similar to when we had radicals, when we were dividing by radicals. So I'm just going to make a note up here to multiply the top and bottom by the complex conjugate of the denominator. So this is whenever you're dividing. So if you look, the complex conjugate is going to be, look at the denominator, rewrite it, but just change the sign. So since the sign is minus, it's going to become plus. So then it's 3 plus 2i. So then you can use the box to multiply these, just remember that there's really parentheses around here, so you have to multiply each piece. So if I do this first piece here, 2 plus I and 3 plus 2I, I'm going to have 6, 4I, 3I, and 2I squared. So up top, I'm going to have 6 plus 7I, because I got to combine these, plus 2I squared. And then on the bottom, those are complex conjugates. So if you remember the rule from the previous page, it's just going to be 3 times 3. And then if you multiply negative 2i times positive 2i, it's negative 4i squared. But it'll always just become positive because, let me just show you. If I do this, this becomes negative 4i squared. But I squared is negative 1, so it's always going to become positive 2 times 2, which is 4. So that's the shortcut, but you could do the box and you'll see that the middle terms cancel if you don't recognize it. If you're afraid that you might mess up the shortcut, then just use the box or FOIL to multiply these out. So now I just have to simplify. So up top I'm going to have 7i plus 2 times negative 1. So this is going to be all over 13. So this is going to be 6 minus 2, which is 4, plus 7i all over 13. So this is fine to leave your answer like that. If it says a plus bi form, then you could write it as 4 over 13, that's your a, plus your b times I. So either one of these would work on a test. Just make sure a plus bi form is really separating it. And then the last example here is when you're dividing by an I. What you can do is, in order to get this to cancel, it needs to become an I squared or a negative I squared. So what we're going to do is we're going to multiply everything by negative I. And that's going to allow this to cancel. So we have up top, we're going to distribute this I. So we're going to have negative 7i plus 4i squared all over negative I squared. And then you're just going to simplify any I squares. So they're going to become negative 1. So we have negative 7i minus 4 over 1. So the only reason why we use negative I instead of I is just so that at the bottom I would have a positive 1, so I didn't have to worry about flipping the signs. But if you multiplied everything by I and got I squared at the bottom and then just had negative 1, that'd be fine. You just had to make sure that you got rid of the negative 1 in the denominator to simplify it. So it doesn't really matter. I just chose negative 1 to make it a little bit easier in the bottom. So then all I need to do is, this is the same thing as negative 7 minus 4, which you just want to flip it so that it's an a plus bi form. And that's it.